Electrothermal industry. A large number of products can only be prepared at very high temperatures. Such type of very high temperature can be attained in an electric furnace, which is probably the most general term used for a group of heating apparatus using electrical energy as a source. Electric furnaces are capable of producing temperature as high as 4,100 degrees Celsius. The high temperature attained in an electric furnace provides two important changes. It increases the rate of reaction, and new conditions of equilibrium are established, as a result of which new compounds not known before the electric furnace have been produced. The three types of electric furnaces, which are arc, induction and resistance. The artificial abrasives, which are silicon carbide, fused aluminum oxide, boron carbide, and calcium carbide. And the miscellaneous electrothermal products, which are carbon disulfide, fused silica, artificial graphite, and electrodes. And then, we begin. Electric furnace is used for heating purpose in various industrial production processes. Electric furnaces are used where more accurate temperature control is required. There are three types of electric furnace, depending upon the manner in which electrical energy is converted into heat. Let's start from the first type of electric furnace, the arc furnace. In the arc furnaces, heat is generated in the electric arc, which can burn only in gaseous atmosphere. To put it differently, the heat in the arc furnace is generated by an electric arc between two or more electrodes, which are usually of graphite or carbon between the electrodes and furnace charge, or between two or more electrode. Electric arc furnace operates under batch process. The arc furnaces are two types, the direct arc furnaces and the indirect arc furnace. In the direct heat furnaces, arc is used to heat a gas in which the arc is burning and the charge forms a part of the electric circuit. In other words, heat is generated directly in the material to be heated. Then we can say that in direct arc furnaces, the charge is a part of the electrical circuit. In the indirect heat furnaces, the arc burns above the charge and the latter does not form a part of the electrical heating circuit. Which means, heat is generated in the heat source, which is separated from the charge, and then heat is transferred to the charge by conduction, convection and/or radiation. Then we can say that in an indirect arc furnaces, the charge is not a part of electrical heating circuit. The second type of electric furnace is induction furnace. Induction furnace operating principle is based on electromagnetic induction and Joule effect. In the figure, it is notable that the furnace consists of power coil, where current flows. As the current flows through the coil, magnetic field is created. This magnetic field produces an electromotive force in a conducting material placed inside the coil. This phenomenon is called electromagnetic induction. Thus, in an induction furnace, heat is generated within the material that is being melted. There is no direct contact between the electric circuit and that of the material. A cooling coil, which permits continuous flow of water, is installed in the power coil side in order to avoid overheating of the power coil during operation. In comparison with electric arc, induction furnace provides a cleaner and safer way of melting materials. Cleaner in the sense that it doesn't use oxygen fuel burners. It is safer because its operating temperature is lower than that of the arc. One of the drawbacks of this furnace is its lack of capability in purifying the melted materials. Thus, the materials that must be loaded into the furnace must be pure and clean. Add on top of that, the material should also be a conductor of electricity. This is seldom used in the electrothermal industries. Induction furnace, like that of electric arc, operates under batch process. The third type of electric furnace is resistance furnace. This is a type of furnace in which heat is generated by passing current directly or indirectly into the materials to be melted or reacted. Electrical resistance furnaces can be operated either batch or continuous process. There are of two types, direct and indirect resistance furnace. In an indirect resistance, the furnace is equipped with heating coils on the side. Heat is transferred to the materials via conduction, convection and radiation. These are commonly used to melt fusible metals. In a direct resistance furnace, this type of furnace in which current is allowed to directly flow into the material. Since heat is generated within the material, very rapid heating is accomplished. Higher temperature on the time scale basis is also obtained compared with indirect heating. This is commonly used in electrical conducting materials. At a previous time, natural products, such as diamonds, garnet, quartz, rouge, kieselpaar, emery and corundum were used as abrasives. In 1891, Acheson produced the first man-made abrasive, known as silicon carbide, in a homemade electric arc furnace. As time passed by, various other abrasives, such as fused aluminum oxide, boron carbide and calcium carbide, were also prepared commercially in the electric thermal furnace. Silicon carbide, SiC, is also known as carborundum, has been widely used as an abrasive and a structural ceramic material. It has a relatively low thermal expansion, high thermal conductivity, high hardness and resistance to abrasion and corrosion. In addition, it has a high force-to-weight radius and high elastic resistance at temperatures up to 1,650 degrees Celsius. These superior properties of silicon carbide made it suitable for applications involving mechanical and thermal loads. Several of these are sandblasting injectors, sandpaper and grindstone, automotive water pump seals, bearings, pump components and extrusion dies. It is also used as material component of heat exchanger tubes. It also finds its application in the electronic industries. Silicon carbide is produced based on the carbothermic reaction, Aikson method. The governing overall reaction is as follows. Silicon dioxide plus 3 carbon to silicon carbide plus 2 carbon monoxide. This overall reaction stems from series of elementary reactions given below. From the overall reaction, silicon carbide production requires silicon oxide and carbon. The source of silicon oxide is quartz sand while the sources of carbon are anthracite, coke, pitch or petroleum cokes. Recent researchers also established the potential of rice husk, which is a rich source of carbon and silica, as a raw material in the production of SiC. The production of silicon carbide starts with a mixing of high-grade raw materials. Sawdust is occasionally added to reduce mixture's density and increase its porosity. High porosity is needed in order to enhance the removal of carbon monoxide and other volatile compounds in the silicon carbide layers formed during the reaction. After blending the appropriate raw materials, the mixture is loaded in an indirect batch-type electric resistance furnace. The furnace consists of a graphite electrode installed at the center. Resistance furnace is chosen because it facilitates the formation of layers, aiding the separation of silicon carbide from the unreacted mix. Fused aluminum oxide, also known as fused alumina, is a material produced by fusing, melting, several oxides, majority of which is alumina, in an electric arc furnace. Impurity oxides contained in the material greatly affects its properties. There are 3 common marketed fused alumina: white, brown and pink ruby fused alumina. White fused alumina, WFA, is produced from high-purity calcined alumina in an electric arc furnace. It is characterized by high hardness, chemical stability, high melting point and large crystal size. However, at high purity, it becomes friable. Because of these properties, WFA is commonly used in applications such as grinding and cut-off wheels, refractories and ceramic shapes, coated abrasives, investment casting shells, laminates, coatings, blasting abrasives, lapping and polishing and many others. Brown fused alumina, BFA, is made by reduction fusion of high-quality bauxites in electric arc furnace. Typical composition is 96.12% Al2O3, 2.70% TO2, 0.67% CO2, 0.11% Fe2O3 and other oxides 0.40%, trade name, Duralum. Its notable properties are high hardness, high toughness, high strength, excellent wear and corrosion resistance and good thermal conductivity. With its indispensable mechanical properties, it is commonly used in applications such as grinding wheels, sandpaper, blasting media, metal preparation, lapping, polishing and grinding. Its excellent thermomechanical properties made it also an excellent raw material in refractory applications. Pink ruby fused alumina, PRFA, is produced by the addition of chromium oxide into high-purity alumina during the fusion process. Chromium oxide imparts the pink color and also increases the toughness of the grain. The toughness of the grain increases as the amount of chromium oxide increases. PRFA is commonly used in vitrified grinding wheels, coated abrasives, blasting abrasives and other similar applications. Production of fused aluminum oxide is similar to that of silicon carbide production. First, the high-quality raw materials are blended into the desired proportion in a mixer. The raw mix is fused in an electric arc furnace at about 2200 degrees Celsius. The melt from the furnace is cooled and allowed to crystallize. It is then crushed to the desired particle sizes. Impurities are removed using magnetic separators and acid washing. This is important because impurities may cause scratch, corrosion, cracks and dark spots on the product. The finished product is then packed, stored and shipped to the customers. Boron carbide, B4C, is the hardest abrasive material ever made synthetically. Its hardness ranks third to that of diamond, first, and cubic boron nitride, second. It was first introduced under the trade name Norbide. Its key properties include high hardness, high melting point, high stiffness and relatively low thermal expansion and conductivity. The hardness and wear resistance of boron carbide made it suitable choice in making nozzles used in abrasive blasting and water jet crushing. It is also used in high-precision tooling dies. It also finds its application in the field of bulletproof vest and anti-ballistic armor. Another notable application of boron carbide is its function in nuclear reactors. This material is used as nuclear shield, control rod and shut down pellets because of its ability to absorb neutrons. Production of this chemical stems from the reaction of boric oxide, boron trioxide, and carbon as given below. Boric oxide is commonly prepared by reacting borax and sulfuric acid in a fusion furnace operating above 300 degrees Celsius. Borax is commonly extracted from seasonal lakes using evapocrystallization process. Production of boric oxide is as follows. All of these reactions took place in the furnace. Water vapor escapes through the furnace opening while liquid boric oxide separates from liquid sodium sulfate as a result of density difference. Boric oxide, being less dense, is then decanted from the mix. Sources of carbon in reaction 6 are activated carbon and petroleum coke. Some researchers also succeeded in using carbohydrate-based raw materials such as table sugar as substitute to coke. The process flow is the same with that of silicon carbide production. High-grade raw materials are mixed completely before entering an electric furnace. The types of electric furnace that can be used are electric arc furnace and resistance furnace. After the carbothermic reaction, the reaction product is cooled naturally. It is followed by crushing in order to meet the product size specification. Magnetic separation is also needed to separate ferrous contaminants from the product. It will be followed by further purification process, chemical treatment, washing, drying, then product storage. Calcium carbide, Ca2, is a compound formed by reacting calcium and carbon in an electric furnace. Part of its properties are non-volatile, non-soluble and easily breaks down with water. It is mainly used in the production of acetylene gas and calcium cyanamide. Acetylene gas can be produced from calcium carbide and water through the reaction. Acetylene gas ready evolved from the solution. This gas is commonly used in acetylene gas cutters, welding torches, and as precursor for the synthesis of larger organic molecules such as polyethylene, etc. Calcium cyanamide can be produced by reacting calcium carbide with nitrogen gas at high temperature according to the equation. Calcium cyanamide is a common raw material in the production of fertilizers. Though metal calcium can be used as the raw material, quicklime, calcium oxide, is more commonly used because it is much cheaper and less hazardous than the former. Quicklime is produced by heating limestone containing at least 97% calcium carbonate according to the reaction. Impurities in the raw materials such as aluminum, magnesia, phosphorus, silica and iron should be kept at minimal level in order to attain high-quality product. Phosphorus should be kept at minimum value because upon reaction it will form calcium phosphide, which easily decomposes by moisture to hydrogen phosphide, a very poisonous gas. Other undesirable impurities are Al2O3 and CO2. Thus, pre-treatment of raw materials is essential. Governing equation in the production of calcium carbide is the bicarbothermal reaction given below. The reaction is highly endothermic, having a standard heat of reaction of positive 110.484 kilocalorie per mole. With this great heat requirement, electric arc furnace is usually used. Process flow in the production of calcium carbide is the same with that of boron carbide. High-grade materials are mixed, reacted in the furnace at 2000 to 2200 degrees Celsius, cooled, crushed, packed, stored and distributed to the target clientele. Miscellaneous electrothermal products. Carbon disulfide, CS2, is a colorless, flammable, non-polar and volatile solvent. Most of the production of this chemical is used in the production of viscose rayon, semi-synthetic fiber, and cellophane, thin plastic used in food packaging. Production of viscose is given below. Its other applications include rubber production, non-polar solvent, insecticide and fungicide. However, due to its toxicity, its uses have been limited to specialized process. Carbon disulfide is produced according to the reaction C+2SCS2RXN15. Carbon source includes charcoal and coke. Solid sulfur containing low ash content is commonly used. Typically used electric furnace is shown in the figure. Sulfur is molten by electric furnace. Further heating result in sulfur vapor which flows up with the charcoal column. Iron sheath serves as catalyst of the process. The carbon disulfide vapor, together with some impurities, the most common is hydrogen sulfide, exits the furnace at the top portion. The product gas is then condensed in a water-cooled condenser. In the condenser, carbon disulfide, having a higher dew point, is condensed while hydrogen sulfide remains in the vapor phase. The carbon disulfide is then stored in suitable containers ready for distribution. It's keen, pure and noteworthy transparent. It expands and contracts very little with changes in temperature. It is the simplest of all glasses, yet for years it was nearly impossible to make pure silica glass. In 1934, Corning organic chemist J. Franklin Hyde came up with a brilliant solution. Glass had always been made by melting dry mineral ingredients. Making a pure silica glass required melting the purest quartz at indeed high temperatures. Hyde's unprecedented idea was to synthesize the glass from liquid chemicals. In a crude experiment, he sprayed liquid silicon tetrachloride into the flame of a welder's torch. It reacted with the water vapor produced by the burning fuel to form an extremely pure glass, fused silica. Hyde had invented a radical new way to make glass, the first in more than 4,000 years, and he hadn't even been given the assignment. Today, his process is used to make fused silica glasses for the most demanding applications. According to J. Franklin Hyde, after you see something work, then you realize that it's not so complicated. The artificial graphite was first prepared by A.G. Aitken by heating amorphous carbon with certain catalysts, such as CO2 or Ai2O3 in an electric furnace at a temperature of about 3000 degrees Celsius. It is known that the industrial process converts amorphous carbon directly to artificial or synthetic graphite in an electric furnace. The furnace used for the manufacture of artificial graphite is an open-top resistance furnace and consists of a core of the coke being graphitized. In electrical industries, graphite is used for electrodes, brushes, contacts and electronic tube rectifier elements. Electrothermal Industries. Thank you for watching.